Dear students, welcome back to the class of 2020 of the course Machine Learning for Healthy Informatics. So I hope that despite the current situation you had a nice Easter break and are now fresh for an exciting new topic. Please, as always, refer to the course homepage for current information. So what will we learn today? The central topic is medical decision making under uncertainty, and we will see what technologies can be of help here. But at first, of course, as always, we do a reflection from last lecture. Then we start with decision making. We will see some basics of graphs and networks and Bayesian networks, and we will do some digressions on Markov processes. Then we will continue with MCMC and deal with the Metropolis Hastings algorithm. That brings us directly to probabilistic programming, an awesome topic, and this is where you have then your next assignment. And we will do some digression here on concept learning. Okay, let's start at first, as usual, the reflection from the last lecture. So as kind of a warm-up quiz, what do you see here? Yes, this is white noise, and white noise is an excellent example for independently identically distributed data, short IID. And technically this is a random signal having equal intensity at different frequency, and this giving it a constant power, spectral tensity, and statistically this is a collection of random variables, all with the same probability distribution as the others, and all are mutually independent. So in machine learning theory, the IID assumption is often made for training datasets to imply that all samples stem from the same generative process and that the generative process is assumed to have no memory of past generated samples. And why do you think this assumption is problematic? Exactly, because in the medical world or in the real world we do not have such. We don't have that in medicine. Okay, next. So what do you see here? Yes, this picture shall envision the curse of dimensionality, here only in 3 dimensions. Originally, this goes back to the work of Richard Bellman in the 1950s. And the problem is that there are so many more possible combinations of the values of the variables than can possibly be observed. And practically, this means that as the number of features or dimensions grows, the amount of data we need to generalize grows also, but exponentially. So this is really a big problem. Okay, last lecture we discussed various data structures, and among lists and graphs we have this data structure. Can you remember this one? Yes, this is a tree, and trees are very important in medicine. So technically a tree is a collection of elements. They are called nodes, one of which is the root, along with a relation, the parenthood, that places a hierarchical structure on the nodes. And a node, like an element of a list, can be of whatever type we wish. And we often depict the node as a letter, a string, or a number with a circle around it. And this is called a dendrogram. Dendrogram comes from Greek dendron, tree, and gramma, drawing. And this is used to illustrate the arrangement of the clusters produced by hierarchical clustering, technically. And dendrograms are often used in computational biology to illustrate the clustering of genes or samples. And this is very interesting. The origin of this dendrogram can be found in Darwin, 1859. Okay, so what do you see here? Yes, this is a mix of different data as seen in the medical domain, and you see it as heterogeneous data sources, the complexity of the data, and the discrepancy between data, information, and knowledge with these various definitions. And this implies that data integration, data fusion, data mapping is very important, as they always contribute a number of various different data to one decision made. And remember please that the combining link is text, because the medical document, the written text, this is the legal binding document. And this is, of course, difficult for machines. So what do you see here? Yes, this is from the early AI field. This is a famous expert system. This was developed by Edward Shortleaf in 1975. This is based on logical knowledge representation, and actually this is an excellent example for a solution in explainable AI, because the user received advice and explanation, so this was quite an advice taker. And most of all of these explanations are retraceable. But my question to you would now be, what do you think is problematic here? Exactly, the ground truths. The problem is that we do not know which facts are true, which are false, and most of all, we deal with the uncertain world. We are living in an uncertain world. The medical domain is not deterministic. And this is problematic now for our machine learning algorithms, because generalization is very hard. Our sensors are very noisy, models are not perfect at all, and logical inference is based exclusively on certainty. But we have not this certainty in the medical domain. Okay, after this warm-up quiz, we will quickly review which machine learning approaches we know. So this is a nice assumption from Pedro Domingos from the University of Washington. So we can, or he could distinguish 5 mainstreams of machine learning. And this is generally good to know, so therefore we briefly review them here. So we start with the symbolic machine learning approach. This is characterized by first-order logic, inverse deduction, knowledge compositions. These are the symbolists. For example, famous symbolists, Mitchell, Magleton, Quinlan. These symbolists mean that all knowledge can be represented. On the other hand, there are the Bayesians, the Bayesian machine learning. This is based on statistical, probabilistic approaches, probabilistic inference, and the Bayesians say that we have a huge uncertainty in the world. So this is typically Judea Pearl or Michael Jordan, David Hackerman, and so on. Then there are the cognitive machine learning approaches. This is they are taking analogisms from psychology or kernel machines. And for example, typically Vladimir Wapnick or Peter Hart or Douglas Hofstadter. And they are really very tightly connected to cognitive approaches. And then there are the connectionist machine learning approaches, neuroscience, backpropagation. This is typically Jeffrey Hinton, Joshua Bengio, Jan LeCun. And then we have the evolutionary machine learning approach, which is based on nature-inspired concepts, for example, genetic programming. So the evolutionarists, for example, John Holland, is based on structured discovery, so evolutionary approaches. Okay, this is quite good to know, this brief overview on these machine learning approaches. Okay, next question to you. Why do you think is this important for us? So this is really a very nice depiction. What do you think? Why is this important for us? Yes, we have mentioned it several times in medical decision making. So, for example, in classification or in diagnosing, there are many situations where the decision must be effective, reliable, retraceable, and thus interpretable. And conceptual simple decision-making models with the possibility of automatic learning, like here, are for a long time in use. So you can see these quick ways here. Actually, this goes back to a decision support tool to the ancient Greek medicine. So decision tree learning goes from observations about an item, these are represented in the branches here, to conclusions about the item's target value, this is represented in the leaves. In our example, you have a root node here and then two branches with several leaf nodes. And tree models are very, very useful and are used in clinical practice for a long time. So this is really very important for us. Okay, so a short historical digression. Whom do you see here? Yes, of course, on the left you see Pierre-Simon de Laplace. You know him well, so he lived from 1749 to 1827. So why is he our hero? Exactly because he laid the foundation for statistical probabilistic machine learning. And on the right hand we see a nice lady, and this lady is a contemporary of Laplace. And I give you a hint, she is a pioneer in computer programming. A programming language is named after her. Yes, this is Ada Lovelace from 1815 to 1852. And she stands for programming in the sense of handcrafted solutions, so hard-coded first-order logic. And the future success will be most probably in an overlapping area, and we will see this on the end of this lecture, that this marriage between those two people would be very beneficial for us. So what I want to say is we need both worlds. Okay, after our first warm-up round, we proceed with our lecture. So, as just a reminder, can you remember what is personalized medicine? So what we mean with the term personalized medicine, we have used the term several times. Maybe you can still remember generalized medicine, one therapy, one treatment for everybody, for all. Then we have, for example, stratified medicine. That means a therapy treatment for a particular group of people. For example, we can separate between men and women as a first step. Yeah, you are laughing maybe now, but usually generalized medicine is a 75 kilograms, 1.60 centimeters high male person. And the first step is to stratify people in different groups, for example, age groups or particular, let's say, groups of people. And the personalized medicine approach is now to find therapies, treatments for one individual person, tailor-made, and exactly based on the personal background of that individual, so genetically, behavioral, and so on. And this is a very nice picture. It shows what kind of healthcare decision should be made, because we are talking about, well, we are always talking about decision support, decision making. And here on the right side, how healthcare decisions should be made. Okay, so what kind of healthcare decisions should be made, how healthcare decisions should be made. Big difference. So on the one hand here, the first P, preventive, so strategies that control risk factors of diseases will be implemented based on a mixture of individualized and population approaches. And Personalized means healthcare decision will be tailor-made based on individualized modeling from genomic to system levels with reference to statistical analysis of a population. Then the next step is participatory. That means healthcare decision making and health information will be shared by individual and relevant practitioners. And here, how predictive risk of developing a disease will be constantly assessed based on the health information accumulated up to date. And the final step, preemptive, that means targets of intervention will be broadened beyond treatment response and remission to maintain and restore body health and functions. And how? Means pervasive. Health services will be available to anyone, anytime, anywhere to facilitate healthcare divisions to be made whenever necessary. So this is the theoretical background of what is personalized medicine. Of course, we are not discussing here economic or managerial issues. So this is just the idea of personalized medicine in contrast to standardized medicine. Okay, but now let's go on. So decision making under uncertainty. So before we start with graphs and graphical models, we quickly review decision making under uncertainty with the emphasis on uncertainty, because exactly graphical models can help here. And of course, as you can see here, the foundation was led by Pierre-Simon de Laplace on the work, of course, of Bayes and Bryce. So, very, very interesting. Yes, this is really very relevant. So relevant that Joshua Bengio, the machine learning guru from Canada, had it in his focus during the last Posner lecture at the NeurIPS conference in Vancouver 2019, December 2019. And actually, he described here the System 1 versus System 2 cognition. And that is a central thesis about the dichotomy between these two models of thought, so System 1 and System 2. And this goes back to originally to Amos Tversky and Daniel Kahneman in 1974. And Amos Tversky died in 1996, but Daniel Kahneman he is still living. He was born in 1934. He's still living, and he received the Nobel Prize in 2002 for this work. So you see this really very awesome work. So the central thesis about the System 1 and System 2 is that the System 1 here, we see this here, is intuitive, fast, unconscious, non-linguistic and habitual. So this is typically how our current deep learning models work. So in System 1, of course, we cannot explain, and this exactly reflects to the current state of deep learning. We cannot explain how we get or we retrieve a solution, okay? While on System 2, this is exactly what future machine learning should do. This is slow, logical, sequential, conscious, linguistic, planning, reasoning. So here you can really explain how you inferred a solution. So this goes towards causality. And we will see in the next lecture a lot of this when we discuss explainability and explainable AI. So you see, this was so important that Joshua Bengio focused on this during his keynote lecture. And this is at the famous NeurIPS conference. Okay, so what is medical action? Yes, it is permanent decision making under uncertainty. So decision making, you see, is central in our discipline, and it is interestingly that explaining, interpreting is a core work in medicine and health. So we use medicine and health synonymously, and we will deal with this in the lecture after your next assignment. So decision making, learn good policy for selecting actions. So this is of utmost importance, always to ask, what is your strategy? What will be the expected outcome? What are your measures? What are your goals? What are your input variables? So the methods to reach the goal in clinical decision making are here from bench. Bench is the evidence from research, the knowledge, state of the art. Then the bedside, this is the experience from clinical practice. And then we have the history, the patient history. This is all information from the past. And then you check it at present, and then you predict. And now you can cite me. This is a proverb which I have always told my students. Past behavior is a good prediction for future behavior. Exceptions are, of course, there because human can be bifurcative. That means that you cannot predict the future, and particularly humans cannot be predicted because humans are sometimes very irrational and cannot predict in time. Okay, so why is decision making so difficult? In practice, clinical decision making is really difficult because it is a triangle of constraints in, for example, knowledge of the doctor, the guidelines from the environment, and ethics, formal policies, and laws, of course. So in practice, the clinicians use decision-making frameworks to guide patient management, to communicate with other healthcare providers, and educate patients and their families. So a number of frameworks have been applied, just that you are aware of that. Okay, so how does a medical doctor now make a decision? So if a physician is asked, how do you make a medical diagnosis? His explanation of the process might be as follows, and this was described already in this famous science paper from 3rd of July 1959. So, Reasoning Foundations of Medical Diagnosis. So, if we ask the medical doctor, he might answer, first, I obtain the case facts from the patient's history, the physical examination, the laboratory tests, and so on. Second, I evaluate the relative importance of different signs and symptoms. Some of the data may be of first order importance and other data of less importance. And then third, to make a differential diagnosis, I list all the diseases with which the specific case can reasonably resemble. And then I exclude systematically one disease after another from the list until it becomes apparent that the case can be fitted into a definite disease category, or that it may be one of several possible diseases, or else that its exact nature cannot be determined. So this is, of course, a greatly simplified explanation of the process of diagnosis. And for the physician might also comment that after seeing a patient, he often has a feeling about the case, a certain feeling which he cannot explain. And the feeling, although hard to explain, may be a summation of his impressions concerning the way the data seem to fit together. And this is the patient's reliability, the general appearance, the facial expression, and so forth. And the physician might add that such thoughts do influence the considered diagnosis. So this is really a complex reasoning process, and that in practice it works not so optimal as in theory has been criticized by the following paper. This is a very interesting paper. This is a very old paper also from 1979 from Anthony Komarov. And Komarov describes clinical data as being disturbingly soft. And what did he mean by the word soft? He meant that this medical data, clinical data, has an obvious degree of variability and inaccuracy. And of course, students, you have now to concern that this is now a comparison between the engineering world and the medical world, and engineering thinking and medical thinking. And this comparison is not that easy because human biology is much more complicated than, for example, our neural network models or whatever. So please be careful when making such comparisons. But taking a medical history, for example, the performance of a physical examination, the interpretation of laboratory tests, and even the definitions of diseases are, according to Komarov, 1979, surprisingly inexact. And data is defined, collected, and interpreted with a degree of variability and inaccuracy which falls far short of the standards which engineers do expect from most data. And moreover, standards might be interpreted variably by different medical doctors, different hospitals, different medical schools, different medical cultures. So that is quite true that it is dependent on where the medical doctor works, in which environment, and which school he is following, and so on. So this is quite an interesting paper by Anthony Komarov, 1979. Okay, so this is the picture. This is the interesting picture from Komarov's 1979 work. Again, it's mostly about explaining, interpreting, and therefore I'm showing this because when later dealing with explainable AI, we will need such information. So here, for example, in order to provide information, a patient must first become a patient, so the patient must perceive himself as sick, but patients have different thresholds for the definition of sickness and or healthy respectively. So for yourself, think of it. And the typical patient dialogue, patient-doctor dialogue uses two types of data, so expressed by the patient or by the doctor and directly obtained from the patient by the doctor. And this is important because we will later learn that the data expressed passes a complex series of perceptive, emotional, and cognitive filters, and this is subject to distortion. So the typical the types of medical data differentiated by Komarov includes expressed data, so verbally expressed objectives, past medical history, current illness description, statements, and so on, and of course verbally expressed subjectives, so feelings, assumptions, and so on. And there is a huge part non-verbally expressed, for example, the appearance, the habitus, they say, the mimic, the gestures, and so on. And and the second type is directly obtained data. So, for example, elements of physical examination, diagnostic laboratory tests, images, pathognomic, signs, patterns, and so on. And I would summarize now, and then I will close this discussion. The big difference between medicine and engineering is that in medicine a substantial degree of uncertainty is inevitable. It may not be possible to acquire the needed data because the measurements cannot be made without destructive consequences for the patient or just for practical limitations, and most of all, think on the length of time required to take adequate measurements and the shortness of time. So in engineering, on the other hand, you have given often adequate resources, and the goal is to reduce this uncertainty strategically to a measurable trivial level and to experimentally demonstrate that the predicted specifications have been met. So please be careful when comparing the engineering world with the medical world. Okay, so how can we learn and infer from data? So remember please how Bayes, Price, Laplace can help here. So we have data, of course, and we have hypotheses. And remember that there can be a lot of hypotheses. So the large H here is the hypothesis space. This can be huge. So you can remember we have discussed this last time. Decision making can be described as searching for an optimal solution in an arbitrarily high-dimensional search space. And however, in medicine, we need not the optimal solution. So often or sometimes is a good solution in short time better, because time is a very, very critical aspect. Okay, so then we have Bayes, and we want to, we have the prior probability. So the probability, then we have the likelihood, and then we have the posterior probability. So we calculate the posterior probability by the prior probability times the likelihood. But if you can remember, we have a big problem, because we have somehow to normalize. We will see this later on, how difficult this is to normalize, to marginalize. And that means that we have to make a division. And this is a problem because, as we have said before, this hypothesis space can be arbitrarily big, and this makes it complex for us. Okay, how do humans make decisions under uncertainty? I go back now to the image by Christopher Wickens in 1984, and you see here this nebula of uncertainty. So this uncertain data is perceived through this selective attention. Then we have form some hypotheses. So this is the same like in machine learning. We have hypotheses, and we check now and we compare the drawn hypothesis with some, let's say, ground truths in the long-term memory, and then we take the best possible action. So it is always to optimize to get the best possible action available, and then you see the outcome, of course, through this feedback, but also through this nebula of uncertainty. So you have a selective attention. So the model of Wickens is still the best model to explain clinical decision making, and most of all to compare it with our technological approaches in machine learning. So this is quite comfortable. Okay, so why is decision making now so hard for machines? So I give you an example, and I spoil now because machines are lacking this contextual understanding, and this very simple experiment by Frank and Goodman will make that clear to you. Absolutely. So if you ask somebody, a colleague of you, to refer to the middle object here, would you use then blue or circle? Which wording would you prefer, circle or blue? So obviously circle. And if somebody talks to you about the blue object, then what would you infer? Is he talking then about the blue or the circle? Yeah, computer scientists do not know this, but from a statistical perspective of reasoning in an uncertain world, we can infer that it is the blue one. Otherwise, you would have circle in mind, okay? So this is one of the most astonishing features of human language, the ability to convey information efficiently in context. Please remember always the word context. For example, each utterance need not carry every detail. Instead, the listeners can infer the speaker's intended meanings by assuming these utterances convey only by relevant information. So this is a very interesting result of this simple experiment, and why I'm showing this to you, because this is the basic for what we learn in the later on course, probabilistic programming, because this is a typical case for probabilistic programming. So here the same people, this Noah Goodman and Frank from probabilistic models. So we will see later that here the probabilistic models and particularly probabilistic programming can help exactly in this question. So absolutely, this is a good example for probabilistic programming when we recursively embed such a model in the speaker model. And then they are going to guess what the output statement might be. So for example, if the speaker, if you can remember, is trying to convey a particular object here. And this is simple Bayesian reasoning, but it's awesome. I think this is really awesome. And before we go into this detail, we will talk about some fundamental basics of graphs, because these are now important for your further understanding graphs. Okay, so at first we start with some elementary basics on graphs. So the mathematicians call it graphs, the engineers rather networks, but these are synonyms. So networks are a general language for describing complex systems of interacting entities. And I will show you that this becomes clear, some examples from nature, but also human-made later on. Okay, so first question, what are probabilistic graphical models, BGM? So this is quite a spoiler. I spoil now the upcoming topic so that we can answer this question before we go into deeper details. So BGM can be seen as a combination between graph theory, probability theory, and machine learning. And this is one of the most exciting advancements in AI in the last decades, with enormous future potential. And this is compact representation for exponentially large probability distributions. And the example question, for example, I give you an example now from biology. Is there a path connecting two proteins? So we see proteins. Proteins are the building blocks of life. Proteins are everywhere in medicine, but proteins are heavily complex and large. And you see, this cannot be expressed in first order logic. Okay, so we start again in 1733. And you see, this is Knigsberg, and the graphs go back to Leonhard Euler. Leonhard Euler 1707 to 1783. And how important Euler for us can be inferred by a statement of Pierre-Simon de Laplace, who said, "Read Euler, he's the master of us all." And what did Euler do? In 1736, he presented a solution to the problem known as the 7 Bridges of Königsberg. The city of Königsberg in Prussia here was set on the Bregel River and included 2 large islands that were connected to each other and the mainland by 7 bridges. 1, 2, 3, 4, 5, 6, 7. And the problem is to decide whether it is possible to follow a path that crosses each bridge exactly once and returns to the starting point. This is the birth of graph theory. And you see here the graph as was drawn by Euler. A graph is a pair. G is V and E, where V is a set of vertices, and so singular vertex, and E is a set of edges, or also links, called links. And these can be directed or undirected. And here the original from Euler. So 252 years later, belief propagation algorithm, Judea Pearl kind of married graph theory with probabilistic theory for causality research, which we will deal later on. And just as a rehearsal for you, belief propagation is the sum product message passing, is an algorithm for performing inference on graphical models like that, such as Bayesian networks and Markov random fields, which we will discuss in a few minutes. So it calculates the marginal distribution for each unobserved node, conditional on any observed nodes. So what do you think here is the problem? Yes, complexity. With 100 binary variables, we have already 2 to the power of 99 possible values. So this is not an easy thing as it might seem at first sight. So belief propagation generally is used in AI and information theory and has demonstrated empirical success in numerous applications, including low-density parity check codes, for example, or free energy approximation and so on. So we will not spend now more time on this, but we will go on to the next slide. So 275 years later, the kind of Nobel Prize in Computer Science, Judea Pearl, for this work received the Turing Award. So he is called the inventor of Bayesian networks, although we know it should be Laplacian networks, but it is called Bayesian networks, famous for causality. And this is now extremely important for explainability, interpretability, as we will see later on. So Judea Pearl actually is famous for his quest on contextual understanding, and I will discuss contextual understanding during this lecture again and again. And Judea Pearl said we must build machines that make sense of what goes on in the environment so they can recover when things do not turn out exactly as expected. So think about that when programming, and you will see how dangerous software programming can be. Causation is actually the programmer's nightmare. So just to illustrate this clearer for you, you have an input 1, so for example, if the grass is wet, it has rained, and an input 2, for example, if we break this bottle, the grass is wet. So the logical conclusion as an output of your program could be, we have broken this bottle, it has rained. And now you can understand how complex it can be in the medical sciences, because this was an easy example. In 2013, due to graphs and due to this is just to demonstrate how versatile graphs are. So protein modeling, coming back again to protein modeling is one of the big challenges, and here for the work on these proteins, these three people got the Nobel Prize in Chemistry in 2013, so it's not so far in the past. And you see, this is pure graph theory. Okay, so first question, where does graphs come from? Graphs can come from various sources. In the following, we will have a look at some of such networks just for motivation. So graphs can be models for networks and graphs as non-parametric bases. So for example, we learn the structure from samples and infer from a flat vector data, for example, similarity graphs, or we encode structural properties, for example, smoothness, independence, and so on. Or on the other hand, graphs as models for networks given as direct input, we will see that now, point cloud datasets given as properties of a structure, for example, as a representation of information. We will see here some examples. Okay, so the first example here, what do you see here? Yes, this is looking at the stars, and this is macroscopic data. Here we see a globular star cluster. This is called NGC 5139, also called Omega Centauri, and this was discovered by Edmund Halley in 1677. And this is what we see here has a diameter of about 90 light years. So the light needs 90 years to travel through this object and includes several millions of stars, and this is approximately 16,000 light years away so from Earth. So look at this structure. This is really awesome, and please consider also the aspect of time, because when our eyes recognize this structure, when you look at your night sky, you see this structure, it might even no longer exist. So please take a moment and think about that. So time and space are, for me, the most fascinating principles of our world. And this is really big data and complexity. Absolutely, yes. So time and space, so the language of nature is mathematics, and what you cannot express in mathematical terms, you cannot measure. This goes back to Roger Bacon, not Francis Bacon, Roger Bacon. Roger Bacon is the monk, 1214 to 1294. And here you see this point cloud data set in arbitrarily high dimensional spaces, and on the left side here we see time, for example, expressed through entropy. And on the right side, you see a representation for space topology, for example. So a Klein bottle, this is a typical synonym for algebraic topology. And you see time and space, the two, and they are very, let's say, interwoven, because we quickly can come to the complexity problem. So as you know, P stands for the polynomial time, and this is the subset of problems that can be guaranteed to be solved in the polynomial amount of time related to the input length. So problems in P commonly operate on single inputs, on lists, for example, matrices, or as also we can occasionally apply this to graphs. So the typical types of operations they perform are mathematical operations, sorting, for example, or finding a minimum, finding a maximum, and so on. And NP now stands for non-deterministic polynomial time, and these problems are ones that can be solved in polynomial time using a non-deterministic computer. And this concept is a little harder to understand. So another definition that is a consequence of the first is often used. NP problems are problems that can be checked or certified in polynomial time. So the output of an NP solving program is called a certificate, and the polynomial time program that checks this certificate for its validity is called the certification program. And now we have a series of NP hard problems, and when is an NP hard problem NP hard? If it is at least as hard as the hardest problems known to be NP. And this leads to two possibilities: either the problem is in NP and also considered NP hard, or it is even more difficult than any NP problem, so it is called NP complete. And this is a big problem for us, and particularly for the medical domain. So think a little bit of that as well. But coming back to protein structure, I show here a shape of a protein. So this is from this large macroscopic structure, what you have seen before, the stars. We switch here to tiny microscopic structures, so proteins, and proteins are organic compounds having large molecules composed of long chains of amino acids. So in a sense, proteins are important for all living organisms, as we know them, and they are used by cells for performing and controlling cellular processes. So, for example, including the degradation and biosynthesis of molecules, the physiological signaling, energy storage and conversion, formation of cellular structures, and so on. So, protein structures, as you can see it here, are determined with crystallographic methods by nuclear magnetic resonance spectroscopy. So, this is a typical image of this. And once the atomic coordinate of the protein structure have been determined, you can put a table of it. You see this here. A table of these coordinates is deposited in large protein databases, PDB called. And this is quite important and quite large. So the shape of such a protein is critical for its function, and because it determines whether the protein can interact with other molecules as well. So protein structures are complex and important, and this is a typical example of that data. Next image, we're getting insight, so knowledge discovery from data. It is essential to make such structures somehow visible to the domain experts so they can understand and gain out knowledge. For instance, it may lead to the discovery of new previously unknown structures in order to modify drugs, for example. So this image is a typical macromolecular interface between proteins, and the transformation of such information into knowledge is vital for prevention and treatment of diseases, and consequently this is a good example for contribution towards personalized medicine. So this picture actually shows a 3D structure of the number seen in the slide before. So this is the tumor necrosis factor, DNF, this is the upper part, which causes the death of the cell, and these are interacting with the receptor. This is the lower part here. So, and the residuals are the macromolecular interface, and they can be visualized here in a ball and stick representation. So this is quite important and a good example for such point cloud data. Okay, another good example for data-intensive and highly complex microscopic structures are yeast protein networks. You know yeast from beer, for example. So yeast is an eukaryotic microorganism, type fungus, consisting of single oval cells, which asexually reproduces by budding, capable of converting sugar into alcohol and carbon dioxide. So this is quite interesting. And there are 1,500 known species approximately currently, and this is estimated to be only 1% of all yeast species. So we don't know a lot about this. Interesting is that this yeast is unicellular, so typically measuring 4 micrometer in diameter. And here in this slide we see the first protein-protein interaction network. This is called Ppi Network. This was produced by Yeung and team from the Parabashi lab, and this is perhaps the most useful yeast. This is really, as it is here, it is used for brewing, for example, for winemaking, yeah, even for baking, and this is known since ancient times. And this Ppi network contains approximately 1,900 proteins as nodes, and they are connected by some 2,300 identified direct physical interactions. And this is derived directly from non-overlapping data, so obtained mostly by systematic two-hybrid analysis. And the nodes are the proteins, you see it here. The links between them are the physical interactions. They are called bindings, and the red nodes are lethal. The green nodes are non-lethal. That means the red nodes are decreasing the organism. The green nodes are letting them grow. And the orange nodes are slow growing, and the yellow one here are not known to date. So this is very interesting. So this protein-protein interaction networks. And the next is the first human protein-protein interaction network. This was by Uli Stelzl. Uli Stelzl is in Graz, actually, professor. And you see these PPIs here are essential for all biological processes. And compiling them provides insights into how this protein functions, how it works. And you see, networks are relevant from a systems biology point of view, and they help to uncover, for example, generic organization principles of functional cellular networks, like here, when both spatial and temporal aspects of interaction are considered, time and space, as I have mentioned before. This is really awesome. Look at this. You can hang this up in your sitting room. This is really awesome. So we see here really the first visualization of a human protein-protein interaction network, and most cellular processes rely on such networks, and a breakdown of such networks is responsible for most human diseases. So actually this is a very, very interesting aspect. So the light blue nodes here, the light blues are known proteins, the orange nodes are disease proteins, yellow nodes are not known yet, yeah. So contrast this image to the slide before and look at the similarities, and also look to the similarities of our star picture. Okay, now that you see that there's also the ability of non-natural network, so this is the block sphere. So while network biology aims to understand the behavior of cellular networks, a parallel field within medicine is called network medicine, and they aim to uncover the role of such networks in human disease. And you see here the similarity to a non-natural structure. Here the visualization of a block sphere, nicely visualized by Hurst, and Hurst mapped this image as a result of 6 weeks of observation, and you see the densely populated areas represent the most active portions of the block sphere. Yeah, and by showing only the links in the graph, we can get a very good look at the structure. Then if we look, for example, at the nodes. And in this image, we are looking at the core of the block sphere. The dark edges show the reciprocal links, where A has cited B and vice versa, you know this. And the lighter edges indicate areciprocal links. So the larger, denser area of the graph is that part of the block sphere generally characterized by social political discussion. So this is a very well-known aspect. Yeah, the final example here in this slide shows the principle of viral marketing. So the idea is to spread indirect messages, which in return suggest spreading them further. So for example, here you have an information object. This blue ball here should be an information object. And then you press the like button, for example, in Facebook or whatever. And a similar process starts, similar to an epidemic in public health, so similar like contagious, yeah. And Sinan Arar here calls this behavior contagion, and it is much of importance for research to know how human behavior can spread, for example, like here. So we can mine, for example, masses of social network data in order to gain knowledge and insight about the contagion of information, which is of interest for the health area, as you know, today, and in particular for public health. So this is a field of public health. So a current trend of research here is opinion mining, where you analyze such data sets. So we have done some own work on this as well. So, okay, so finally that you see the usefulness for medicine. This is a famous example by Barabashi. So a disease is rarely a consequence of one single abnormality in a single gene, but it rather reflects the perturbations of the complex intracellular network. And here you see these emerging tools of network medicine. They offer a platform, for example, to explore systematically the molecular complexity of particular diseases. And this can lead to the identification of disease pathways, but also to the molecular relationships between apparently distinct pathological phenotypes. So this is really very cool. So advances in this direction are essential to identify new disease genes and to identify drug targets and biomarkers, for example, for complex diseases. So summarizing in this slide, we see a human disease network. So the nodes are the diseases. Two diseases are linked if they share one or several disease-associated genes, and not shown here are small clusters of isolated diseases. So the node color here directly reflects the disease class of the corresponding diseases to which they belong. Cancers, for example, appear as blue nodes here, for example, and neurological diseases are red ones, red nodes, yeah. And the node size correlates in this image with the number of genes known to be associated with the corresponding disease. So you see, you have now a very brief overview on some examples. Just as a teaser, we switch now to the probability side of the networks, and this is called Bayesian network. So what you should now know at first is Bayes nets are convenient representations for encoding dependencies and conditional interdependence. So Bayes nets, I have put it in this Gänsefüßchen here. So BNs, these are graphs plus parameters. So this defines joint distributions over variables, and you can calculate everything else from that. So through inference is also possible. So reading conditional independence relations from these graphs. So Bayesian nets are very versatile. And of course, I have to give you some book recommendations. If you really want to go deeper, I recommend these books. So for example, David Barber from University College London, and the classic is from Daphne Koller and Nir Friedman from Stanford here, the probabilistic graphical models, the Bible, so to say. So this is really, if you want to go deeper into this, because I can only scratch here the surface. So I have to emphasize this is such an awesome, interesting and challenging field that I only can touch the surface, but I can motivate you to go further. So because these probabilistic graphical models, they discuss a variety of models and spanning Bayesian networks, undirected Markov networks, discrete continuous models, and so on. But another book recommendation would be Chris Bischoff from Microsoft Research Cambridge. So this is pattern recognition machine learning, and there's chapter 8, and exactly chapter 8 you can download for free because it is a sample chapter, and it's highly recommended. It's very easy to read. And finally, causality. This is the professor, Judea Pearl, the professor of computer science and statistics at the University of California in Los Angeles, and he directs the Cognitive Systems Laboratory, and he conducts research in artificial intelligence, human reasoning, and he's the Turing Award winner, and is really very awesome. So if you have time, have a look at it. Okay, so what are the rules of probability? So maybe as I cannot emphasize it often enough, this is the basic work of Laplace, although it is called Bayes. But what do you think? What is the most important assumption of probability? I give you a hint. The probability of an event and the negated opposite of that event is equal to 1. And this can be expressed by, yes, correct, by the sum rule. So this is a very powerful tool, the sum rule. And the same applies to the product rule. So the same that applies to the sum rule applies also for the product rule. You see here the product rule. And the sum rule and the product rule is a corollary. So actually this what we see here is a corollary of the sum rule and the product rule. And this is called the Bayes rule. Yeah. And of course we have then to normalize so that this is our denominator then. And this is really awesome. With this is the basic. So please remember, most quantities in machine learning for health informatics are non-deterministic. So the problem is always to deal with stochastic, with incomplete, with probabilistic data, and of course information. And probability theory allows us to deal with exactly these problems of the real world. So this is really very important. So I cannot remember you often enough about this. Okay, before we continue, we do a digression, so a crash review on Markov processes. You know it for sure from other courses that a Markov chain is a stochastic model describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. So in continuous time, we know it as Markov process. And this goes back to the Russian mathematician Andrei Markov. Markov lived from 1856 to 1922. Okay, so why are Markov decision processes so important? Because Markov decision processes, short MDP, are random processes in which the future given the present is independent of the past. So this is quite awesome. Think about that. So this is quite interesting. And one of the most important classes of random processes. So this is really very versatile, and that you believe me, I have a good example for that. So before the Go hype, the DeepMind people here, this is the people around Demis Hassabis, they worked on applying deep networks to reinforcement learning. I hope you remember Space Invaders. This is an old game. And the DeepMind people tried to learn this game just by observing the screen. So this is very important to note. Just by observing the screen, so the states of the screen, okay? And they developed an agent, and the agent observes the current screen, the actual screen. This is the observation, yes. And the task is partially observed, and many emulator states are perceptually aliased because it is impossible to understand the current play situation from only the current screen state, as you can obviously understand. And therefore, you need sequences of actions and observations, and you use this as input for an algorithm, and which learns the game strategies depending upon these sequences. And all sequences in the emulator are then assumed to terminate in a finite number of time steps. And this formalism gives a rise of large but finite Markov decision processes, and in which each sequence is a distinct state. And as a result, you have then the action, so you can apply standard reinforcement learning methods for these Markov decision processes simply by using the complete sequence as the state representation at the time t. And this is optimization. So this is typically machine learning to maximize the reward. And this leads to the famous Nature paper of the DeepMind. And actually, this group became famous just by learning to play a game from the screen state. So you see how you can come into nature with machine learning. Okay, from where do we know such behavior? So remember this, please, from our last lecture on the expected utility theory. I have the slide here again for you because this is very important. We have discussed this in slide 47 in the first lecture. So actions may have long-term consequences, actions, and reward may be delayed, of course, and sometimes it might be better to sacrifice immediate reward to gain more long-term reward. And the typical example is financial investment, where the effect may appear in many months or even in years, okay? So the principal goal here is to maximize the total future reward, and this is remarkably similar to human behavior. And all this was studied already in classic AI. So we have a 50 years of classic history about this. So this is very, very interesting. And you see, this was the expected utility theory. This was published by John von Neumann and Oskar Morgenstern in 1944. We use it again. So this is the classical model. This is the famous paper by the Littmann group. And these are still the reinforcement learning gurus, and they go back to cybernetics, and they studied models of optimal behavior of learning automata, as it was called at this time. And interestingly, and this is very interesting, all these ideas came from human psychology. For example, Hilgard and Bauer in 1975. And this algorithm here, this goes back to Bellman in Princeton on dynamic programming, and we will see this again in our probabilistic programming approach later on. So this is very, very interesting. Okay, what has a reinforcement learning agent to do now with Markov decision processes? So reinforcement learning problems involve an agent interacting with an environment. Okay, so far so clear. The agent must learn about the environment. So we see it here. We have the agent. But the agent must also discover how to act optimally in this environment. And hence there is both a statistical component, so learning about the environment here, and the computational component, deciding how to act. And in reinforcement learning, the environment the environment is typically modeled as a controllable Markov process. So the agent must solve a Markov decision problem. And reinforcement learning can therefore be viewed as the study of traceable approximation algorithms for solving Markov decision problems. This is really very cool and very interesting. So we can summarize this together for you. Intelligent behavior arises from the action of an individual seeking to maximize its received reward signals in a complex and changing world. So, reinforcement learning, types of feedback, this is crucial. So, one really crucial step on the decision of machine learning is on the decisions of machine learning feedback. And there are three kinds of feedback: sequential versus one-shot, sampled versus exhaustive, and evaluative versus supervised. And in machine learning and examples of learning problems, for example in bandits, as you can see beautifully here in this nice table, reinforcement learning, contextual bandits, supervised machine learning, they result from their combination, which is seen here. So the problem formulation in Markov decision process. So reinforcement learning lost ground through the 1970s, but was picked up by computer scientists recently. And now it became a central idea of studying in machine learning. So the term reinforcement came from referring to a generic reward signal that needs to be predicted over time instead of the activity of strengthening a behavior response. So classic learning problems could still be discussed in this way, but the door opened to a wide avenue for further research in Markov decision chains. So Markov decision processes specify setting and task. Planning methods use knowledge of P and R to compute a good policy, which is called Pi. And this may be our brain learns like that. So Markov decision process model captures both sequential feedback and the more specific one-shot feedback. So when, for example, this P of S given S and A is independent of both S and A. So this is one of these recent trends. So the agent observes the environmental state at each step of the time. So here is an example where the agent has full observability. So the agent directly observes the environment here and his state. And this is such a typical Markov decision process. So here the main problem is that even if S, the large S, is fully observable, it may contain noisy, irrelevant and useless information, or even in the medical domain, wrong information. So please remember always that a Markov state contains the information from the history. The future is independent from the past given the present. And this can be a real disadvantage. Think on transfer learning. Okay? So the agent state is the agent's internal representation. So this is just to show that the agent state can be any function of history. And the history, as be seen below, is a sequence of observations, actions, rewards, all observable variables up to the time t. And you can see this is like a sensimotor stream of robot data. So for example, this is typically used in autonomous driving, autonomous vehicle. And the value function is the prediction of future reward and is used to evaluate the goodness or badness of states and therefore to select between the actions. So these are these typical RL agent components: the policy, the value function, the model. And what if the environment is only partially observable? So a good example here is a robot. Think on a robot relying only on computer vision. It's your vacuum cleaner robot or whatever. and which is not aware of its current location. Or think on a more easier daily thing, poker play, only public cards are observable for the agent. And this is that the agent must construct its own state representations S. Yeah, now back to Bayesian networks. After this digression, we go back to our original trail, so back to Bayesian networks. So just that you have a general overview on these three types of probabilistic graphical models. So first we have this undirected, so for example for computer visions, or directed Bayes nets. This is very useful for designing models, or this factored, so useful for inference and learning. So these three types of probabilistic graphical models are used. And what is a directed Bayesian network? So we can now answer. Now we are ready for clearly define a Bayesian network, and here a directed one. We just take this because I show you a clinical practical example of applying this one a little bit later on. So a directed Bayesian network is a probabilistic model consisting of two parts. First part, a dependency structure, and local probability models. And this can be expressed through a fully connected direct graph and expressed by this equation, and where Pa of xi are the parents of xi, and Bn, the Bayesian network, inherently models the uncertainty in the data. So they are really a successful marriage between probability theory and graph theory. And so what is a directed Bayesian network? It is a model, a multidimensional probability distribution in a sparse way by searching independency relations in the data. And this model allows different strategies to integrate two data sources. So example, directed Bayesian network with 7 nodes. So this is the absence of edges conveys also very useful information. The main question remains, which joint probability distribution does such a graphical model represent? We look at the clinical case example for this. Let us look at the typical medical case. Here, this slide shows the MRE of a breast cancer, and this is the 12 centimeter fixed mass, and an important task in clinical patient management is, of course, to determine a prognosis for a patient that suffers from such a disease. So this is really very, very important. And we define prognosis as the prediction of the future course of a disease conditional on the patient's history and the projected treatment strategy. Think what I have shown you before. What is your strategy? What is your goal? And the danger is, of course, we are always dealing with probable information. This is non-trivial. And therefore, a valid prognostic model can be of great benefit for clinical decision making and of great value to the patient, of course, for notification of and quality of life decision. So these data are not always available, and the only source of knowledge may be that of the domain expert, which is often condensed in the form of medical textbooks, guidelines, or procedures. So how can one predict the future on past data and present status? So you can probably guess all this can be modeled by graphical models. So this slide depicts the representation of such a clinical decision-making process on time, and the interaction between a patient and a physician in terms of the model of how the physician makes decisions and a model of how the patient responds to these decisions. So, of course, with respect to the prognosis, the medical professional wishes to predict or part of predict the state of the patient for a future time period. So they therefore need to take into account how the state of the patient changes under the influence of choices made by the physicians. And this implies, of course, that we must predict how the physician will respond in the future. That means we have to know the treatment strategy under which the physician operates. So remember, ask always your medical doctor, what is your strategy? And most traditional prognostic models sidestep the explicit representation of time by mapping the current state of the patient directly into the future. And this temporary nature of a problem is often essential to clinical decision making. We know that. So clinical data such as patient history, laboratory analysis, ultrasound parameters, these are the basis of a day-to-day clinical decision support and are often underused to guide the clinical management of cancer, in this case, in the presence of microarray data. So, yeah, and note please now, the current patient state influences, of course, the physician's decision, which in turn influences the next patient state as well. So it's, unfortunately, it's not that easy. So back to our breast cancer example, this is the probability table now. So we have local probability models. They specify how the variables depend on their parents. And here in this case, they use discrete valued Bayesian networks, which means that the local probability models can be represented with the conditional probability table, CPT. In this slide, we see the features, including 5 factors from the patient history, 4 factors from the physical examination, and 4 factors from the mammographic findings here, yeah, distortion, mass, microcardial asymmetry, and so on. So here you see the big picture. This slide summarizes the aforementioned things and shows the big picture of such a Bayesian network to diagnose breast cancer. So the first layer includes 5 features related to the patient's clinical history. The second layer contains 1 diagnostic feature, breast cancer, and the third layer involves 8 features from the both mammographic findings and the physical examination. And this was the state of 1999. This was in absence of the genetic treatment, which is, or genetic analysis, which is now state of the art. So 10 years later, we have this integration of microarray data. So prognostic markers of breast cancer metastasis to ensure that newly diagnosed patients receive appropriate therapy are now in operation, are now very important. And within the last years, these studies have demonstrated that the potential value of gene expression signatures in assessing the risk of developing a distant metastasis is very important. So, however, I must say, due to the small sample sizes of these individual studies, the overlap among signatures is low, and their predictive power is often limited, of course. Yeah, but integrating microarray data from multiple studies in order to increase the sample size is therefore a promising approach to the development of more robust prognostic tests. So here, robustness is also a very, very important wished effect. So here you see these graphical models for this genetic case along with the conditional probability tables. So the conditional probability tables here, they specify the probability that the variable takes a certain value given the value of its parents. And in these slides, we see an example of a Bayesian network with 4 binary variables. And the prognosis variable in this example has 2 parents. So this is gene 2 and gene 3 here. And the CPTs for each variable are shown alongside each node. You can, of course, this express in a computer. Okay, the concept is the Markov blanket. So the Markov blanket of a variable A is composed of the variable's parents, its children's, and its children other parents. Here the Markov blanket variables are shown in a gray circle. And in machine learning, the Markov blanket for a node A here in a Bayesian network is the set of nodes A composed of A's parents, its children's and its children's other parents. So in a Markov network, the Markov blanket is a node and is set of neighboring nodes. A Markov blanket may also be denoted by MB. Okay, so Previously, we mentioned that the discrete valued Bayesian network consists of two parts. So consequently, there are two steps to be performed during model building. This is structure learning, which you can see here, and learning the parameters of the CPT. And here you see, so this slide must be seen together with the previous one, of course. And here you have a step-by-step explanation what this procedure does. The best is to read the paper along, and you can do this in peace at home during the night, for example, or so on. So I will skip that now for now. So this takes too much time now. Okay. Also, the second step is described here, but you will be curious what this is all about and can read it along. So this is the outcome. So this is the complete Bayesian network for the best model using this partial integration of clinical and micro data. The Markov blanket of the outcome variables is indicated by the triangles here with the white nodes here. Okay, and yeah, this is most promising. This partial integration method is most promising and has an independent test set area under the ROC curve of very high value, so above 0.85, and after choosing an operating point, the classification performance is better than frequently used indices. So, inference in Bayesness is intraceable and be complete. We have mentioned that this is one big problem, that we can run quickly into NP-hard problems. So, there's of course approximate solutions. And when somebody argues about the human in the loop and the non-perfect solution, remember that in clinical medicine we have a huge time constraint. It's the famous 5 minutes. And often it is better to have a good solution within time than a perfect solution too late. So what have we learned so far? Graphical models are a marriage between probability theory and graph theory. They provide for us a natural tool for dealing with two problems that occur throughout applied mathematics and engineering. This is uncertainty and complexity. And this is particularly important for the medical area. Yeah? And in particular, they are playing an increasingly important role in the design and analysis of machine learning algorithms. So fundamental to the idea of a graphical model is the notion of modularity. So a complex system can be built by combining simpler parts. This is very, very important, and I cannot often emphasize more. Probability theory provides for us the clue whereby the parts can be combined, so to ensure that the system as a whole is consistent and providing ways to interface the models to the data. And the graph theoretic side of graphical models provides an intuitively appealing interface by which humans can see that and model highly interacting sets of variables, as well as the data structure that lends itself naturally to the design of efficient general purpose algorithms. So it's really a good thing. So we continue with the digression about the connects of graphical models and decision making. So what classes of graphical models do we know? Now it's easy for us to summarize. We know already directed, undirected graphs, and there's an overlap in the middle. You can see that here, the bright red zone. That is called a chordal graph. So this is a decomposable graph. And you have here this Markov random fields. This is also called Markov networks here. And here it is DBN. This is dynamic Bayes nets. Please do not mix this up with deep belief networks, what you have surely thought about These deep belief networks developed by Geoffrey Hinton. No, these are not. These are dynamic Bayes net. Although I have to admit that dynamic Bayesian is also a bad name, because a dynamic Bayesian network is a way to represent a stochastic process using a directed graphical model. So it is also slightly misleading, because the network is not dynamic. The structure and the parameters are fixed So it is just a network representation of a dynamical system. So please, this is a big difference. Okay, so here the so-called plate notation, where we assume that the data is IID, independent, identically distributed, and this assumption is shown in this notation. So left, the data points x are conditionally independent given the theta parameter, and this is the left is the same, right is the same as left, and repeated, the nodes are drawn inside a box, and this box actually is called plate. So the large letter n here specifies the number of repetitions of the xi node, x index I node. So mathematically this can be expressed by the equation on this right side, which is the joint probability distribution of theta given the data. And learning usually means computing a maximum of the parameters given the data, so argmax, maximum or minimum. Most often it's maximum, yeah. And the pi here, this pi here is a multinomial parameter vector in the stationary distribution of a Markov chain. For more details, you should really consult the Kevin Murphy book, page 321 and so forth, to read more about the details. So I just want to mention this plate notation because this you will see in the papers and so on. So you have to know that structure. Okay. So this is a naive Bayes classifier. Okay. So just that you have an example from biology again. So proteins, of course, what else? Proteins and their different graphical models. So here different protein structures, and here the different graphical models. So this is really a nice slide which shows you the dependencies. Okay, remember please, hot topics. Medicine is an extremely complex application domain, dealing most of the time with uncertainties. So we always are confronted with probable information. When we have big data but little knowledge, so most often we have big data but little knowledge, sometimes we have small data and little knowledge, automatic machine learning can help to gain insight, because structural learning and prediction in large-scale biomedical networks with probabilistic graphical models, this is really a hot topic at the moment. And if you have really little data and deal with NP-hard problems, we still need the human in the loop, the expert knowledge. So there's no way out. When dealing with NP-hard, we need the human in the loop. And from structure to function prediction, so high-throughput genome-wide molecular assays, they probe cellular networks from different perspectives. This is now central in molecular biology, state of the art. And probabilistic graphical models here are useful for extracting meaningful biological insights from the resulting data sets. And these models provide a concise representation of complex cellular networks by composing simpler submodels. So the procedures based on the well-understood principles for inferring such models from data, they facilitate a model-based methodology for analysis and discovery. And this methodology and its capabilities is illustrated by several applications to gene expression data. So there's a nice paper on this in the Journal of Machine Learning Research. Okay, so the next paper presents a new method to infer protein networks from multiple types of genomic data. So the central hypothesis is that most biological functions involve the interactions between many proteins, and the complexity of living systems arises as a result of such interaction. Awesome, really awesome. And in this context, the problem of inferring a global protein network for a given organism means using all genomic data of the organism is one of the main challenges in computational biology. So this is a really hot topic, and I'll give you an example. So is graph isomorphism NP complete, for example? This is very important for health informatics, so discovering relationships between biological components. This is an unsolved problem in computer science. Can the graph isomorphism problem be solved in polynomial time? So far, no polynomial time algorithms know. It is also not known if it is NP complete, but we know that subgraph isomorphism is NP complete. So finally, a practical example of all this. So we continue now with an absolute awesome topic, and interestingly one of the oldest topics in computer science and also very important for machine learning nowadays. So it's a little bit confusing that there are so many different terms for one and the same thing. So often they are used interchangeable, but let's figure out how it works. So what is the problem with observable data D in the real world? So we have the data D given the theta parameters. So note please that the variables of course could be always different. So in every paper it's different. Sometimes it's X, Y, theta, even pi. So you can use any symbols. They are not, there's no fixed rule, unfortunately, yes. So often we want to calculate characteristics of a high-dimensional probability distribution. So for example, this way. Yeah? And the posterior integration problem is that almost all statistical inference can be deduced from the posterior distribution by calculating the appropriate sums, which involves an integration. So this is an integral. And this is hard, as you can believe. Yeah? And actually, this problem of learning and inference is going back to statistical physics. So the posterior is the likelihood, the posterior is the likelihood times the prior through the evidence. This is the marginalization. But this is the sum over all hypotheses, as we have learned before and we have heard several times. And this is high dimensional and this is a complex problem. So for continuous variables, this is absolutely difficult and unsolvable. And this is a very important problem in statistical physics. So what was the origin of MCMC? So the origin was in 1944 when they worked on simulation samples in Los Alamos. And this is the Nicholas Constantine Metropolis, 1915 to 1999. Then this is Julius Robert Oppenheimer, 1904 to 1967. This is von Neumann, you know him from importance sampling. And this is Enrico Fermi, 1901 to 1954. And actually Fermi had the idea and they introduced the Monte Carlo method, although they were in California at this time. And I often ask myself why not called it Las Vegas method, because Las Vegas was so little at the time and had no significance, but Monte Carlo was very famous. So what are now Monte Carlo methods? Of course, Laplace was the first again. So it is a class of algorithms that rely on repeated random sampling. And the basic idea is using randomness to solve problems with high uncertainty. And in 1781, Laplace has already described this principle. Yeah? And this is for solving multidimensional integrals which would otherwise intraceable. So this is really a key to many, many problems. And this can be used for simulation of systems with very many degrees of freedom. So DOF is degrees of freedom. For example, fluids, gases, particle collectives, cellular structures. You can see this on tumor growth simulation, for example. So MC connects computer science with cognitive science and many other areas. So we can use it for solving problems of probabilistic inference involved in development of computational models, and as a source of hypothesis about how the human mind might solve problems of inference. So therefore it's called often Bayesian brain, the human mind, the probabilistic inference machine. So you see MC connects computer science beautifully with cognitive science. And for a function f of x and distribution p of x, the expectation of f with respect to p is generally the average of f when x is drawn from the probability distribution p of x. And in the formula you see this is the expectation, and you have seen this already. This is the sum of over all the function and the probability distributions. So we can now, and you can remember, normalizing is a very hard task, and it is very important, and also for the finding of global maxima and global minima, for example. Particularly global minima here, as you can see here, is a very hard task. And you can use this now as a stochastic optimization. Think on a Brownian motion, for example. And the problem itself may be stochastic as well, as for example planning under uncertainty. But you can use this, and you can solve many problems with this expectation maximation. And in electrical engineering, this is also called ergodic problem. And ergodic is a stochastic process. If it is statistical properties can be deduced from a single sufficiently long random sample of the process. So the reasoning is that any collection of random samples from a process must represent the average statistical properties of the entire process. So in other words, or easier expressed, regardless of what the individual samples are, a bird's eye view of the collection samples must represent the whole process. And of course, conversely, a process is not ergodic, is if a process that changes erratically at an inconsistent rate. So this is really an awesome step. Okay, so what can we do? For example, a random walk. This is a typical example here. So use it as physical simulation, counting many things as fast as possible, and you can compute eigenfunctions and so on. And the notation, so we have the expectations of a function of f and xy with respect to a random variable x. This is denoted by e of x. And please remember the part on expectation maximation, so in the first lecture. And in situations where there is no ambiguity as to which variable is being averaged over, this will be simplified by omitting the suffix, for instance, ex. Yeah? And if the distribution of x is conditioned on another variable set, then the corresponding condition expectation will be written like that, given set. Similarity variance is denoted as variance of f of x, and for vector variables the covariance is written covariance xy. Okay, so global optimization, what is the main problem? Integrating is a hard task. We have learned now, at least for our von Neumann machines, and time is critical, particularly in the medical domain. We have also learned this, so this becomes important. So the general goal of this is to find the points of a domain of a function in which the function values are maximized. So where it is argmax. Remember, the sum sign sigma can be replaced by the integral continuous function. And we can have now this as normalization, as marginalization, or as expectation. And what do you think is the main problem here? Yes, of course, the integrals, they become rapidly intraceable, and what does it mean? It cannot compute it within reasonable time, so we need these algorithms. And the practical example here is Metropolis Hastings algorithm, and many machine learning people say that this is the most important algorithm ever since. So what is it? So there's a paper, so this is Nicholas METROPOLIS, and he published together with a guy called Stanislav Ulam, and they reported about this Monte Carlo method, and they received moderate citations. So I've looked it up on last week, this week, 6,500. So for a paper of which is on the market since 1949, I would say this is not so many, okay? But interestingly, the later paper has to date enormous 41,000, so nearly 42,000 citations, And interestingly, if you read this paper has only 5 pages and no references at all. So this should not, I shouldn't show it to you, because you should not be motivated to write sloppily without any citations. And for the sake of completeness, I show you the paper of Hastings by 1970. This is the generalization and Monte Carlo sampling methods using Markov chains and the applications. So this is a real very good summarization of all this before. And so what is this Metropolis Hastings algorithm then doing? I can imagine that you are most anxious to know what this famous MH algorithm does. So again, Metropolis is the original version. Metropolis Hastings is a general version. So the Metropolis Hastings algorithm can draw samples from any probability distribution P of x, provided that we know a function f of x proportional to the density of P, and the values of f of x can be calculated. So this is a fact, yeah. And the requirement is that f of x must only be proportional to the density rather than exactly equal to it, makes the Metropolis Hastings algorithm particularly useful, because calculating the necessary normalization factor is often extremely difficult in practice, as I have shown you before. So this is really very useful, and we can show this in the next, right? What is importance sampling in general? So importance sampling is a technique to approximate averages with respect to an intraceable distribution P of x. The term sampling is arguably not a misnomer, since the method does not attempt to draw samples from P of x. So we can summarize, rather the method draws samples from a simpler importance distribution and then reweights them such that averages with respect to P of x can be approximated using the samples from Q of x. And the Gibbs sampler is an interesting special case of this Metropolis Hastings. As Gibbs sampling is a simple and widely applicable Markov chain Monte Carlo algorithm and can be seen as a special case of this Metropolis Hastings algorithm. By the way, Josiah Willard Gibbs, 1839 to 1903, was the first PhD in engineering in the United States at Yale. So, the Gibbs sampler, this enjoyed an initial surge of popularity. Okay. So, how to learn now modular structures from network data? So, this is a really nice work presented at the ICMLR 2014 by Elham Azizi from the University of Boston, and this shows how modular structures are learned from node variables. For example, gene expression and network data. Yeah, you have here the gene expressions, here the network data, and the node variables are color coded, ranging from green low to red high, and the number of parents are assigned to each module. These are the orange links here. Yeah, and on the next slide we see the graphical model of this approach. So you can now see what we have learned before. So this is the graphical representation of the model before. The assignments of nodes, so to modules A and parents of modules S, represent modular dependency structures from which we observe node variables xc, x index c in each condition c, and network data B, R to N in P index R to N between a parent R and a node N. And this means the node variables my C here are determined from parent means my RC with mixing coefficients gamma determined based on parent split point Z. Okay, so this is a very nice paper in the International Conference of Machine Learning, ICML. Okay, how can we estimate the parameters using this now in practice? So here a typical algorithm of this class. So this is a common strategy for dealing with hard Bayesian learning problems. This is performing MCMC simulation. And recall that these methods, that in these methods we construct a Markov chain whose state is the assignment to all unobserved variables, such as the stationary distribution of the chain and the posterior probability over these variables. So in our case, the state of the chain consists of theta and h, and we need to ensure that the stationary distribution of the chain is the desired posterior distribution. So this is really a good example, but now I think you will be curious and ask why should this be relevant for medicine. So I show you a nice application. So as you see here in this picture, this is the Mycobacterium tuberculosis gene regulatory network, and the inferred program in the figure before, in the slide before, shows that either of the two regulators can repress the expression of these 48 genes assigned to this module, which include lipases and genes involved in fatty acid beta oxidation and triglycerines cycle metabolic pathways. So an expert can infer a lot out of this. So an alternative approach, this is also a good example for graphical models and deep multi-task learning. So here, for example, discrete time modeling of disease incidence with MCMC. So a good general example for the usefulness of both MCMC and the Metropolis Hastings here for the modeling of measles, measles, not corona, measles. So the pattern of measles epidemic, this is here, is in developed countries before vaccination, is one of the best documented population cycles in ecology. The measles are very well documented. So here you see an actual example. So finally a current practical example shall demonstrate the usefulness and versatility of Metropolis, Hastings and MCMC. And the best is again, if you have a look at the original paper by following the link I have given it, and this can be viewed free. So in this work, the Metropolis Hastings algorithm has been used to estimate the parameters in the model by carrying out the Markov Chain Monte Carlo procedure. And the authors of this very recent paper developed a discrete time stochastic epidemic model with binomial distributors to study the transmission of the COVID-19 disease. This is now this corona, or as the correct name is SARS-CoV-2, because the name is severe acute respiratory syndrome. So this is SARS, and this group of viruses are known since 2000. And the model parameters here are estimated on the basis of fitting the newly reported data from January 11 to February 13, 2020 in China. And the estimates of the contact rate and the effective productive number support the efficiency of the control measures that have been implemented so far. And these simulations show that newly confirmed cases will continue to decline and that the total confirmed case will reach the peak around the 8th of February 2020 under the current control measures. And this was then true at the end. This is a good example how this model shows that reducing exposure, of course, is the most effective measure to control the spread of the disease. And this is, students, this is exactly what we are doing now. So sitting in chambers, although I have to admit that I prefer teaching in the classroom. So I would like to stand now in front of you in the classroom and discuss with you in real time. But it is how it is. So we continue. So, finally, to prepare you for the next assignment given by Florian Endl, a very short introduction to probabilistic programming from the top-level view. So please be careful, because this name can also be misleading. This is not about writing software which behaves probabilistic. It encompasses tools for probabilistic modeling. This is very important to mention. Okay, book recommendation. All good things comes in 3. I think the most classic book is this from Avi Pfeffer. now working for Charles River Analytics. This is practical probabilistic programming. I think he's one of the gurus, worked together with Daphne Koller in Stanford. So this is really very good. This is a practical book, Bayesian methods for hackers. And I would really recommend to have a look at this book from my colleague Fabrizio Riguzzi from Italy. So Fabrizio Riguzzi is a colleague and wrote this excellent book, Probabilistic Logic Programming extends logic programming by enabling the representation of uncertain information by means of probability theory. So probabilistic logic programming is at the intersection of two wider research fields. It is the integration of logic and of probability and probabilistic programming. And you know, this is a successful marriage again, and we as Austrians believe in that marrying is an excellent strategy. So what have we learned so far? What is probabilistic programming? Let us answer this. So what have we learned so far? Probabilistic thinking is a valuable tool for decision making. This is really very, very important to know. Overcoming uncertainties is the huge success currently in machine learning and AI, of course, AI. Probabilistic reasoning is a versatile tool, so it can be used for many, many different problems. And PPLs, so probabilistic programming languages, are domain-specific languages that use probabilistic models and the methods to make inferences in those models. So you have now a really nice definition of what is probabilistic programming. And the magic is in combining probability methods with representational power. So this is the real magic in this. Okay, so there are a lot, of course, for different approaches for this. So you will learn that later on. So, for example, on PyMC. PyMC is a Python module that provides tools for Bayesian analysis. So you can do probabilistic programming with it. But you can have a closer look by your own at this. I give you a medical example because you will be curious what you can do in this Bayesian Laplace approach. So suppose, for example, you have a series of DNA sequences and you want to predict the outcome from any arbitrary sequence of it. Oh, this is a typical case. So if you know such probabilities, you can create a variety of scoring models for arbitrary input sequence to help predict the experiment outcome. Now, the question is, how do we get the probabilities? Now, for example, you can infer it from maximum likelihood or the better maximum a posterior, so MAP, Bayesian approach. So here. Then D is the observed data. This is the experimental data from the scoring model parameters. Then you specify the prior distribution of the nucleotides. And then you specify the experimental data and you have the posterior distribution of the nucleotides. So this is really a nice example provided by Dan Williams from Life Technologies, Austin, Texas. Okay, finally, before we finalize today, a brief digression on concept learning, because I have mentioned concepts now so often, but what is concept? What is a concept? What is concept learning? So we quickly make a digression on this. So question, when is a cat a cat? When is a cup of cup? This goes back to a very good work from Brunner, Goodenough and Austin. They published a study of thinking, and this became the landmark in cognitive science and has much influence on machine learning up to date. So they write about rule-based categories, and the concept specifies conditions for membership of this category. So this is really very awesome. And what is concept learning then? Concept learning is highly relevant for machine learning research, concerns the factors that determine the subjective difficulty of concepts. So why are some concepts psychologically extremely simple and easy to learn, while others seem to be extremely difficult, complex, or even incoherent? And these questions have been studied since the 1960s, but are still unanswered. So how human learners extract rules from patterns of data and the relative subjective complexity of different kinds of rule. This is central to the investigation of human learning from cognitive science, and this is very, very interesting to transfer this knowledge into machine learning research. So here you see a good fit of cognitive science to machine learning, computer science. So how can we model basic cognitive capacities as intuitive Bayes? So this is actually really a good example for the usefulness of Laplace. Again, yes, I know we should say Bayes. I know we say Bayes. This is modeling of gesunder Hausverstand, I would say. So we all do this all the time. You have an hypothesis H around the world, about the world, for example. So you have this hypothesis about the world around you, or a cause. You have given observed data X, here X, and you have a background theory about that, call it T. T, this can be your set of expectations. Please remember what we discussed on the model of Wickens in the first lecture. And now we score each hypothesis by computing the posterior probabilities. So the likelihood P of X given H and T times P of H given T. And now we have the problem, now we need Metropolis Hastings again, but now we have to marginalize, and we can then, so the computational challenge here is the normalization. We have to divide the above term through the evidence here. And you know, this is extremely difficult in the real world because we have a large hypothesis space, can be very, very many hypotheses, and the probability distribution thereof can be large. But you can now infer the posterior probability, and this theory-based Bayesian framework, as it is called, provides a formal means to address fundamental questions about human cognition. So, for example, to answer questions of human knowledge at multiple levels of abstractions. How can abstract domain knowledge guide learning of new concepts, for example? Or how can abstract domain knowledge be learned? Or what conceptual resources must be built in innately, as a big question? Or how do mechanics of statistical learning and inference interact with and operate over structured symbolic knowledge? And traditionally, computational accounts that aim to explain a broad spectrum of human cognition have focused exclusively on either sophisticated inference processes or sophisticated knowledge representation. So this is the main work of Josh Tenenbaum at the MIT and his group. And I will show you a quick, a very easy experiment. With this experiment presented by the Tenenbaum group, it will become very clear to you how super our human mind works and how bad our best algorithms are currently, and that we are far away from this human level AI. So look at this slide. This is pure fantasy objects, and now I give one arbitrary chosen object a name. I call it Quaxel. So I call it Quaxel and ask you, can you identify other Quaxels on this slide? So this is obviously a Quaxel and this is a Quaxel. Now look for yourself. Can you identify further Quaxels? Maybe this is a Quaxel and this is a Quaxel and this is a Quaxel. So you are now able, in a fraction of a second, you have understood the concept of a Quaxel and you can generalize it. So you are able to build rich models of the world and make strong generalizations from input data that is really sparse, noisy, and ambiguous. And in many ways, far too limited to support the inferences we make. So how do we do that? And the answer is we don't know it. So this is the state-of-the-art research. So we don't know how this can be done from the humans. And I just show you that this is still state of the art. So this is understanding, context understanding. So our mind make inferences that appear to go far beyond the data available. And why I'm showing it to you, this is a science paper, famous science paper, and they show what I have shown you previously and all the way down. So this is basic base price Laplace. So this is the theory 250 years ago. And our mind make inferences that appear to go far beyond this data. And this MIT group described approaches to reverse engineering human learning and cognitive development, and in parallel engineering more human-like machine learning systems. So you see computational models that perform probabilistic inference over hierarchies of flexi-structured representations can address some of the deepest questions about the nature of human thought. So our main question here, how does abstract knowledge guide learning and reasoning from sparse data? What form does our knowledge take across different domains and tasks? And how is this abstract knowledge itself? So if you have time, please read the work of the MIT group around Josh Sternbach. This is really awesome, and is really deep in machine learning theory. So what is then probabilistic program induction? So we still have to learn what is induction. As you know, supervised learning, function approximation is to make assumption from data and to generalize. And exactly this generalization is a fundamental problem in machine learning. So it is all about induction. Opposed to the deduction. And maybe we rehearse it quickly. So induction is forming a generalization based on what is known on the observed data. So for us, interesting is to add probability. So probabilistic induction, for example, I give you an example when we would now be in our lecture hall at the TU Vienna. So you go, hopefully soon again, to the Mensa in the Freihaus, and you observe that 4 out of 6 of your colleagues of this course order the same vehicle. So from your observation, you induce that the vehicle is probably good. And then you decide to try it yourself. So induction is at play here, since your reasoning is based on an observation of a small group as opposed to universal premises. Yeah, this is induction. Deduction is the conclusion follows from general premises, and in deduction the truth of the conclusion is guaranteed by the truth of the statements or facts considered. And finally, abduction is you see an half-eaten vehicle on the student's desk, and abduction will lead you to the best possible explanation. So your reasoning might be that your student colleague ran to the underground as he was late and left the vehicle behind, so you create an explanation. So it's always trouble to discriminate deduction, induction, abduction. So I think I should point you to the Latin roots. So ducere means to lead. The prefix d means from. So in means to or toward, and induction leads you to a generalization. So the prefix ab means away, and you take away the best explanation in abduction. So I would really ask you to learn this thoroughly, because this is fundamental for understanding machine learning. Okay, so what is now the difference between deduction, induction, abduction again? So deductive reasoning, you have the hypothesis, observation, and you draw logical conclusions to go from the general to specific, proven correctness. The danger, the hypothesis must be correct. So the deductive reasoning defines whether the truth of a conclusion can be determined for that rule based on the truth of premises. A equals B, B equals C, therefore A equals C. Inductive reasonings makes broad generalizations from specific observations, so specific to the general, not proven correctness. The danger, it allows a conclusion to be false if the premises are true. But we can generate hypotheses and use deductive reasoning for answering specific questions. And abductive reasoning is inference to get the best explanation from an incomplete set of preconditions. So given a true conclusion and a rule, it attempts to select some possible premises that, if also true also, may support the conclusion through not uniquely. So you know this is the famous example: when it rains, the grass gets wet, the grass is wet, therefore it might have rained. This kind of reasoning can be used to develop a hypothesis, which in turn can be tested by additional reasoning or data. Okay, my question to you now: which of these one is written by a human and which one was drawn by an algorithm? So which one is from the machine, 1 or 2? Yeah, maybe you have guessed correctly. It is 2. You just have to believe me, or better, the authors of this paper. And why I'm showing this? Because this is what can be done by probabilistic programming. So this famous paper, Human Level Concept Learning Through Probabilistic Programming, used probabilistic programming. And what can a Bayesian program learning framework do? This is just an example what can be done. So it is capable of learning a large class of concepts from few examples and generalize it in a way that you were unable to tell me what was done by a human and what was done by a machine. So I think now that you are curious to get your first assignment on probabilistic programming. So here again, this is highly relevant for medical decision making under uncertainty, because we can infer abstract causal principles to capture dependencies among observable variables. So here you see this abstract knowledge in a simple medical domain can be represented using a graph scheme, as we have learned before, a probabilistic generative grammar for graphs. The variables fall into 3 classes: risk factor, diseases, symptoms, with causal influences only from risks to diseases and diseases to symptoms. So given a newly observed correlation, for example, between working in a factory and chronic chest pain, the graph schema generates a constrained set of hypotheses for how that data might be explained, shown in red here. Yeah. So this is very relevant for us, and as you can see here in the right side, we can use graphical models to infer the number of classes, which variables are in which classes, and what kinds of relationships hold between classes. And this can be done directly from the data. So we will learn about this when we deal about this explainable error stuff. The question of how abstract causal principles, for example framework theories, might themselves be learned is a major open question in both artificial intelligence and cognitive science. Okay, concluding, so we are at the end of the lecture. So concluding, just that you see how our graphical models can help. For example, does a relationship exist? If yes, how strong? So cognition can be seen as a probabilistic inference in visual perception, in language acquisition, in motor learning, associative learning, memory, attention, categorization, reasoning, causal inference, decision making, and the theory of mind. So causality, learning concepts from example, learning causation from correlation, learning and applying intuitive theories, balancing complexity versus fit. So this is now the last slide, and I would like to thank you for listening. Now you are hopefully well prepared for your probabilistic programming assignment. I hope you are now excited about this topic. I thank you for taking this course. Please stay healthy, and we hear again. Thank you very much.